Welcome to Statistics. It's Thursday, April 16th, and today we're going to talk about inference for population proportions. But a little housekeeping first. I hope you've seen my message about your options for the final exam, and remember to check out the assignment in which I've asked you to specify whether you want to take the final exam or not. That's due by Sunday at 11 p.m. And if you have questions, just email me. I'll be glad to help you out, let you know where you stand in the class, and so on. Okay, let's go ahead and jump into it. So, we've been doing inference so far for quantitative variables, things like the amount of cereal in a box, or the body temperature of an individual, and so on. Those are all quantitative variables. But there are situations in which you want to do inference for a categorical variable. And when you do that, you typically want to find out what proportion of the population of interest falls in a certain category. So, as usual, let's begin by looking at an example that's of this type. Monmouth University recently polled a simple random sample of 857 adults nationwide, and this occurred from April 3rd to April 7th, so a little more than a week ago. Of these 857 individuals, 377 said that they approved of the president's job performance. That is, 377 out of 857, or 43.99% of the respondents, approved. So, what can we say about the president's job approval rating among all U.S. adults in this time period? The situation here is similar to the kinds of inference we've seen in the past. That is, we have information from a sample, namely that about 44% of this sample approved of the president's job performance. But we want to make an inference from that and say something about what proportion of all U.S. adults would say that they approve of the president's job performance. So, this is a classic inference problem because we're inferring from sample data something about the population at large. But the difference is this is not a quantitative variable we're talking about. We're talking about presidential approval. If somebody asks you whether you approve the job of the president, you don't answer with a number, you answer with a yes or no. So that's a categorical response that you give. And that's why this is a different kind of inference than we've looked at so far in the past. But what you'll see is that the procedure for doing the inference follows along very closely with things we've seen in the past few lectures about inference for quantitative variables. Let's break it down. So, in this particular situation, there is a population parameter that we're interested in, and we're going to call that P. That would be the president's true approval rating among all U.S. Adults. And that's unknown. But we do have some information about it, and that's our sample statistic, which I'm going to call P hat here. That's the 377 out of 857, the proportion among the sample, in other words, who approved of the job the president's doing. That's about that 44% we saw. So, what does that sample statistic, P hat, 43.99%, tell us about the population parameter P, the true proportion who approve of the job the president's doing? Well, just at sort of a gut level, we would be comfortable saying that, presumably, that the true proportion of all adults is somewhere near 44%, but we wouldn't want to say that it's exactly the same as the sample proportion. So the kinds of inference we would do here kind of follow along with the kinds of inference we've seen in the past. That is, we could use our sample proportion p hat to make an estimate for p, and that would be a confidence interval. Or we could use our sample proportion p hat to evaluate a claim for p about p. For instance, if somebody claims that the president's job approval rating is uh, greater than 50%, we could see, does that claim hold up in the light of the evidence we have? That would be a significance test for p. So in order to work with this, we need a little bit of theory, and that, as you might not be surprised to learn, comes from the central limit theorem. The central limit theorem gives us the sampling distribution of p hat. And what it says is that p hat has an approximate normal distribution for large sample sizes. In fact, the distribution becomes more and more normal as the sample size gets larger. And this is the same sort of thing as we've seen for x bar in the past. Moreover, the central limit theorem tells us that the mean of the sample proportion p hat is equal to the population proportion. So that would mean that the sampling distribution of p hat, the way that p hat varies across all possible samples of the same size as ours, that distribution is centered on the right value, that is, the true population parameter p. Of course, that's unknown, but what this information tells us is that our sample statistic p hat is an unbiased estimator for p, because on average, its average value across all possible samples is equal to p. Furthermore, we can determine from the central limit theorem that the standard error of p hat, that is, our estimate for the standard deviation of p hat, is given by this formula here. That is, you take p hat, multiply it by 1 minus p hat, divide by the sample size n, and then take the square root of all that, and that's our estimate for the standard deviation of p hat. And with those two things in hand, we can go ahead and find a confidence interval for p. So a level at C confidence interval for the true proportion p is going to be our point estimate, p hat, plus or minus a margin of error m. And so the confidence interval will look like p hat minus m up to p hat plus m. The margin of error is, as we've seen in the past, a critical value times the standard error. And the standard error of p hat was given in that formula on the previous slide. And z star comes from the standard normal distribution. It's that critical value from the standard normal distribution corresponding to the confidence level C. So we don't use the t-distribution here when doing inference for proportions. And that's essentially because in a proportion problem, the basic variable is categorical, and so there's no standard deviation associated with it. We only use the t-distribution when there's an unknown standard deviation that we have to contend with. So let's use this to find a 95% confidence interval for President Trump's true approval rating among all U.S. adults nationwide based on the Monmouth University data. So again, our point estimate for p would be our sample proportion p hat, that 377 over 857, or about 43.99%. Next, we can compute the standard error, which is the sample proportion times 1 minus the sample proportion over the sample size, all under the square root. So you do that math and you get about 0.1696. I'm rounding things to 4 significant places here. Of course, when I do the work on my calculator, I don't round at all to avoid unnecessary round-off error. Then we compute the critical value. Our confidence level was 95%, so we're looking for this upper bound of the middle 95% of the standard normal distribution. Remember, the critical value for a confidence interval for a proportion is a z star value. It comes from the standard normal distribution. So in the usual way, we find this is the inverse norm of 0.975, and that turns out to be 1.9600, again, rounded to 4 places. The margin of error is the critical value times the standard error. So in this case, that turns out to be 0.03323. So what this means is that the margin of error for 95% confidence is about 3.323%. The 95% confidence interval then is our p-hat value plus or minus that margin of error. And so that turns out to be from about 0.4067 to 0.4731, or if you express it in terms of percentages, the confidence interval extends from 40.67% up to 47.31%. So our conclusion would be that based on the sample data from this poll, we're 95% confident that the president's true approval rating among all U.S. adults nationwide is between 40.67% and 47.31%. So that's the basics of computing a confidence interval for a proportion. I wanted to show you the website where I got this data, because it's a really good sort of amalgamation of a lot of the polling data that's out there from a bunch of different pretty reputable sources. And that is the website pollingreport.com. So I'm just at their homepage here. You just pollingreport.com, just search for that, and it'll be the first link that comes up. And they have polls on just a host of data. Let me take you to the polling data for President Trump. And so you get, there's just a host of polls here, but the presidential approval polls are in the job ratings category. And so here you see a list of all the recent polls done by a bunch of different polling organizations about President Trump's approval rating. And the one I used was the Monmouth data, simply because it was among the most recent. And if you click on that, it'll take you to it. And there you see the actual results of the poll that we just analyzed. 857 people responded, an approval rating of 44%, margin of error of 3.4%. We got 3.3. So Monmouth University was being a little conservative. They put a little bit higher margin of error, just by 0.1%. But that's where those numbers come from. And you can just see there's a wealth of data here going back not only to the week of April 3rd through the 7th, but all the way back into last year. And so you can see how they keep track of all that. Another good site for polling data is 538.com. You may have seen that. Here, they use somewhat different methods. They use bootstrapping methods and randomization methods that we really haven't gone into at all in our course to look at presidential approval. But notice their result is pretty consistent. They're reporting a 44.2% approval rating for the president currently, which is pretty consistent with our 43.99%. And they also track it through time and so on. Their methods are a little different. They take into account many different polls, and they weight the polls based on their historical performance. So the whole polling arena has gotten vastly more sophisticated over the last, I would say, 10 to 15 years with the advent of big data and sort of computational methods for statistics. And so it's an active area now, but already, based on what we've done this semester, we're beginning to get a grip on the kinds of methods, at least some of the kinds of methods that are being used. All right, I'm going to sign off now. There will be a homework on this material. I'm going to make it due Saturday night, just so you have some time to get in touch with me if you need to about problems. I hope you're well. Do not let that date slide for your response about whether you want to take the final or not. Again, that's Sunday at 11. Uh, and in the meantime, y'all take care, and I will be back in touch with you soon.